Okay, what I'm going to show you right now is the design I made for two-way slab without beams, or some says this is also called the flat slab. So this is analyzed by the direct design method. So in this calculation I'm going to show this is in English unit, but I'm using MathCAD worksheet, so there's no problem in converting units. But anyway, so this is the sketch right here. So this shaded portion is called the design strip. Okay, we will be defining all of this. First, we will have a column dimension of 16 inches. So that will be equivalent to 0.4 meters. And then we have a partition weight of 20 psf, or pounds per square foot, and a service live load of 40 psf. We have a compressive strength of concrete of 4000 psi, that is normal weight concrete, and yield strength of steel of 60,000 psi. The design strip width is 14 feet and the span is 18 feet. So this is the span center to center of the column along this design strip. And then the clear span in the long direction, we have the span. You just deduct the width of the column, or the dimension of the column, of 16 inches, so that will give us 20 inches. So the calculation, and for the calculation and discussion, first we have to determine the minimum thickness of the slab, or in this case the flat slab. So we have a table here. This table is from the ACI code, table 9.5C, for the minimum thickness of slabs without interior beams. So this all depends on the yield strength of steel you're going to use. So just locate here. So in this case we're using the 60 KSI yield strength, so we have without edge beams, and we are in the exterior panel. Okay, so you might want to use ln/30 for your minimum slab thickness. So we got here 6.66 inches. So in this case we're going to use the 7 inches slab thickness. Next, we will check the shear strength of the slab. So we need to calculate the effective depth. That is, we're going to consider the concrete cover. We were using the concrete cover of 3/4 of an inch, and then we're going to use later on the diameter of the rebar. We're going to use the number 4 rebar, so 1/2 inch. So that would give us an average effective depth of 5.75 inches. The slab weight is, we calculate that here, slab weight, and then the factor dead load is 1.2 multiplied with the total of self weight and the partition weight, so that will give us 129 psf, and the factor live load 1.6 times the service load, so that will give us 64 psf. So the total factor load is 193. So we're going to investigate for the wide beam action for the wide strip at the distance d from the face of the support in the long direction. So we're going to analyze a 1 foot width. So this is a generic calculation for the wide beam action. for the checking of the shear. And then in this calculation, this is the check for the two-way action, or the punching action of the checking for our the thickness of our slab. So in this case, all are passing for the wide beam action and as well as for the two-way action. So that means the preliminary design indicates that 7-inch slab is adequate for control of deflection and shear strength. So next, we're going to check the applicability of direct design method. So direct design methods have limitations. It's not all the time you can always use the direct design method according to ACI code 13.6.1. So there is a minimum of 3 continuous. If you want to use the direct design method, your layout should have a minimum of 3 continuous spans in each direction. Long to short span ratio of not greater than 2. Successive span lengths are equal. Columns are not offset. Loads are uniformly distributed with service live to dead load ratio of not greater than 2. So in this case it is okay. And slab system is without beams. So if these checkboxes are all ticked, that means you're good to go on using the direct design method. So next, we're going to calculate the factored moment in slab. So we have here the total factored static moment and static moment per span. That is considering the design strip. So this is the total factored static moment per span. And then the distribution of the total factored moment MO per square per span into negative and positive moments, and then into column and middle strip moments. This distribution involves direct application of the moment coefficients to the total moment MO. So there's calculation based on the stable. Stable is from the ACI code. So you just need to locate the exterior and exterior negative, the positive, and the interior negative for the end span, as well as the positive and the negative for the interior span. So that's pretty much it. This is the computation for factored moment in columns. For the columns, you need to take into consideration these values right here when you are designing the columns. But that's another topic. We'll proceed here. The number 5, check the slab flexural and shear strength at exterior column. The total flexural reinforcement required for design strip. Determine reinforcement required for strip moment. So we got here the generic calculation for that, as well as for the check slab reinforcement at the exterior column for moment transfer between the slab and the column. So we got here the generic calculation for that. So what we got in our design, I highlighted here. Provide 3 number 4 bars by concentrating 3 of the column strip bars, 6 number 4 bars within the 37-inch slab width over the column, and then for symmetry add 1 additional number 4 bar outside of 37-inch width. So note that the strip section remains tension controlled with the additional 1 number 4 bar. So this is the calculation for the reinforcement required for the middle strip. The same procedure, but we're going to use the moment for the middle strip. yeah, so that's pretty much it. So this is the illustration or the arrangement of the rebars that we got from our design calculation. Okay, so once again, that is the sample calculation I made for the two-way slab without beams analyzed using the direct design method. Thank you, and see you next time.